Okay, so before you went on spring break, I introduced you to generalized linear model. And of course, generalized linear model gave us an opportunity um, in a way that the distribution of response variable may not necessarily be normal. Okay, it could be Poisson, it could be binomial, and so on, like that. So, which means with the generalized linear model, is gonna give it provide an opportunity to model different kinds of data. Okay, in the general linear model, where we consider linear regression, of course, the assumption of the probability distribution of the response variable was normal. But what if in a situation where we got a count data, or we got categorical data, that's the distribution is no longer going to be a normal. Of course, the generalized linear model actually provide us a framework in which we actually going to have more flexibility when the nature of the response variable is not normal. And of course, I remember the other time, um, you know, the GLM actually uses the probability distribution from exponential family. Okay, I presented to you the other time an exponential family. I show you how a probability distribution of a response variable can follow exponential family. From the exponential family, we're able to derive link function. The link function is very, very crucial in a generalized linear model, because the link function enables us to relate a transform expected value of the response to the systematic part. Okay, I show you how to derive the link function for Poisson. How to do, because you derive a link function for Poisson to be used in a Poisson regression model. We derive a link function for binomial distribution to be used as a logic in the logistic regression model, and so on like that. I walk you through all of that. But you know what? And I also remember I walk you through one of the regression type in the generalized linear model. I walk you through logistic regression. Okay, logistic regression is one of the family in the generalized linear model. I remember before we went on spring break, I walk you through how to interpret logistic regression model. But you know what? What we want to do today is, how do we measure model performance in generalized linear model? When I talk about generalized linear model, I'm talking about how do I know my model is going to do a great job when I'm working with the logistic regression model? How do I know my model is going to do a great job if I'm working with a Poisson regression model? How am I going to know my model is doing a great job if I'm working with the negative binomial regression model? How do I know my model is going to do a great job if I'm working with other variants of logistic regression model, like a multinomial logistic, like ordinal logistic, and so on like that? So because of that, I want to introduce you to goodness of faith. Okay, the goodness of faith measures how well the model fits the data. Okay, now how well the model fits the data? I'm actually going to compare the fitted model, that is the fitted model using the generalized linear model. Okay, I'm going to compare that with a saturated model. Please, I need you to pay attention. When I say saturated model, what do I mean by saturated model? Okay, the saturated model is a theoretical model that fits the data perfectly. I'm going to say that again. A saturated model, it's a theoretical model that fits the data perfectly. But you know what we want to do? We want to compare our fitted model with that. Okay, we want to compare our fitted model with a saturated model. It is called a saturated model because it's a theoretical model that fits the model that fit the data perfectly well. Okay, in a saturated model, the number of observation is equal to the numbers of parameter. When the number of observations and the numbers of parameter are the same, that's a saturated model. We can't do that in a real life because there will be problem of over parameterization. But you know what? It's just like you want to play, like those of you that play a game with computer, you play in against computer. Has anybody played that game before? Where you play against the computer. Has ever won when you play with the machine? Who has won before? Okay, so it's more or less like we want to compare our fitted model with the saturated model. Okay, now what do we use? We use deviance. In the generalized linear model, if we want to talk about model fitness, okay, we actually use deviance. Don't forget, in the general linear model, when I say general linear model, probably I'm referring to linear regression, where the response variable follow normal distribution. Of course, what do we use as a model fitness in that regard? We use sum of square or residual. We use R squared. But right now, we're talking about generalized linear model. Okay, we're actually using deviance. So when I say deviance, the deviance is a way to compare the fitted GLM with the saturated model. The saturated model is a theoretical model that fits the model perfectly. Now, when I say deviance, okay, now take a look at this. The deviance is actually, it uses, let me tell you this. When you are using the GLM, the generalized linear model, okay, now the reason why um it rely on the distribution of response variable from exponential family is because we normally make use of a method of maximum likelihood in the estimation. Because the method of maximum likelihood is used in estimation. Okay, now because of that, the deviance is more or less using a likelihood ratio test where we compare our fitted model using the G that is separated within the GLM platform with a saturated model. And that's why you see the is equal to 2 multiplied by the difference between the likelihood associated with the saturated and that of the fitted. And that is what you're seeing here. Okay, the equation. Okay, now if you take a look at that, okay, we're actually gonna see y and y cap. Y, okay, is the y and y cap, like I said, the y cap is the values of y predicted. And of course, the Y is the actual response. And of course, for sufficiently large sample size, okay, and if the distribution of the response variable you specified is correct, then the deviance follow chi-square. I'm going to say that again. If if the sample size is sufficiently large and the response variable you specify is binomial, and if it is correct, it's going to follow chi-square. And let me also tell you this. We can also use deviance to compare nested models. When I say nested models, if I'm looking at the effect of age, okay, and gender, okay, maybe one model, I'm looking at the effect of maybe a one model, I'm looking at the effect of age on, on the risk of having disease. Okay, maybe in one model, I'm looking at the effect effect of age on the risk of having disease. And in another model, I'm looking at the effect of and gender, age and gender on the risk of having disease. Okay, the first one is going to be a simpler model. The second one is going to be complicated model. Okay, because here I got two predators, age and gender, but here I only have age. The first model that is simpler model is nested in the complicated model. I can also use a deviance to choose which of this model is appropriate. If I'm going to choose, if I'm going to do that under the non-hypothesis is only going to support the simpler model. The alternative is going to be complicated. And of course, if I fit this, call this model 1, and I fit this, if I call this model 2, okay, if I want to do that in R, I'm going to do ANOVA into model 1, comma, model 2, test equal chi-sq. The test equal chi-sq. Okay, this is going to give me a p-value that I'm actually going to use. Okay, so all what I'm trying to say here is that deviance can also be used to decide between two competing models, okay, that are nested, okay, and that follow chi-squared. Okay, now let me say this. We got different kind of deviance. We have a null deviance. Please pay attention. I needed to pay attention. We have a null deviance and we have residual deviance. Let me first talk about the null deviance. In the null deviance, we are actually comparing the deviance of saturated model, okay, with a model without covariance. I'm going to say that again. Null deviance compare saturated model with the most simplest model. When I say with most simplest model, it means with an intercept model without covariance. Maybe here, okay, I'm only looking at the risk of having disease. I'm not looking at the effect of any covariate at all. That's a null deviance. Okay, when null deviance is very high, okay, when null deviance very high, then it means that I need covariance. Okay, now I just wanted to take note of that. Now we have other ways. Passing chi-squared is another way to measure the distance between the fitted model and the saturated model. Okay, that also follow chi-squared. Okay, we can use the AIC, the BIC, and so on like that. Okay, but I think I should briefly talk about residual variance as well. Okay, let me also, before moving to example, I'm going to talk about residual variance. Why no deviance? Sorry, I want to talk about residual deviance because we have two types of deviance, like I said. Okay, we have no deviance and residual deviance. I'm going to write that now. No deviance, residual deviance. The null deviance compare saturated model with the intercept model without covariate, while residual deviance compare saturated model with the model with covariate. Does that make sense? Okay. Now, I want to go into an example, okay, and I need you to pay attention. I want to go into an example, and I need you to pay attention. Now, I want to use a baby food example. Okay, I wanted to see how deviance work play out. Okay, now you see here the number in each case we have 6 cases. The first case 77 have disease, 381 without disease, and of course we're also considering uh, categorical effects of sex, and of course the type of food. And here, if I want to know the totality from case 1, I'm actually adding the number of disease to no disease. Any question on this? Okay, now because we are having either having disease or not having disease, of course, the yi will follow binomial distribution. Of course, you all know binomial distribution is actually used to model, outcome with two possible, model variable with two possible outcome. Okay, now, like I said here, n is the number of unique profiles, okay? But N is not the same thing as summation Ni. I needed to pay attention. N, not the same as summation Ni. You can see here the Ni here, you see it's 458. So if I add all this N1 to N6, it's not the same thing as 6. That is what I wanted to know. Now, because each case can be modeled using binomial, I'm actually going to write the probability mass function for binomial. Can you see that? Okay. This is the probability mass function for binomial. For case 1, we can use binomial. So Ni combination Yi pi I, take a look at that. Where do I get 458? The total number in case 1, can you see 458? When I added the number of disease with no disease, okay, and there after then the pi 1 minus pi 1, which means what I'm looking for in that particular case 1. What is pi 1? The pi 1 represent the probability of having disease in that case 1. Okay, now if I want to do that, I need the knowledge of likelihood function. So if I have a probability distribution, the likelihood function is having the joint probability. This guy means products, the joint probability, which is what you have here. Now, if I have after writing the likelihood, don't forget, I told you, the generalized linear model rely on maximum likelihood estimation. And that is the reason why whatever the distribution of the response variable, I need to write the likelihood function for it. Now, this is the likelihood function for binomial. Then, because I actually want to maximize, and the likelihood function is a product of probability mass function, okay, it will be problematic to maximize multiplicative functions. And that is the reason why we normally take the log. Taking the log of likelihood will enable us to have an additive, the likelihood to have an additive structure that can be easily differentiated. Does that make sense? Optimizing likelihood function is the same as optimizing the logarithm of likelihood function. Okay, now I have a logarithm of the likelihood function here. Take a look at that. Then I can easily, optimize that. Okay, now, but you know what? We have a way to do this in R. If you have your data set, okay, and of course, we specify binomial family. Of course, this is a logistic regression output. If you take a look at the logistic regression output based on the data, you can see here. Now, there's something I also to pay attention to. In a GLF family, take a look at that. You're going to see Z value. In the conventional linear regression, it used to be T. Pay attention to that. Now, based on this, and you know what? If you take a look at this, sex girl, which means there are two levels. Okay, sex boy has been reference. Okay, then we have three levels of food. Here is only reporting food, breast, and food supply. Don't forget, we don't want to run into domain variable trap. And that is the reason why if I have K levels of category, it's going to be K minus one. Does that make sense? Okay, now I need you to pay attention. But I'm seeing a lot of exam questions here, midterm two. You know, we actually counting down now. Now, if you have these outputs, how do we predict why using the feeder model? The very first thing we need to first obtain the feeder model based on what I have here. Okay, the feeder model is this. This is pi cap equal to that. Okay, you know, don't forget, we also have in a logit form. If you want to write it in a logit form, you're going to write log. Please pay attention. Log pi, log pi cap divided by 1 minus. Don't forget, that was a link function that we derived the other time from the exponential family for binomial. So you know that guy equal to what? That guy equal x beta cap. Okay. Do you know that if I solve for pi cap, this is what I'm actually going to have? The first one that I wrote is in logit form. Logistic regression result can be presented in two forms. Number one, in logit form. Number two, in probability form. Please pay attention to the two. One in logit form. The logit form is a log pi cap divided by 1 minus pi cap equal to that. And the other one is in probability form. Okay, now, if I want to predict y, in binomial distribution, if y follow binomial, what is the mean of y? NP, you remember? In the lower level statistics is NP, right? Now, if it is NP, here our P is pi cap. So take a look at this. The y cap supposed to be equal N pi cap. Pi cap represent the P. Okay, now I need you to pay attention now. Okay, situation where I'm interested in, situation where I'm actually interested in boys bottle feed. Okay, now take a look at this. If you take a look at this, okay, and you take a look at this. Oh my God. What is that intercept? What it is in the intercept? It is sex boy. Don't forget, gender has two levels. Arrow is displaying the one for girl, then it means the one for boy is in the intercepts. Not only that, if you look at the type of food that we got three type of food. I'm going to show you, but arrow is showing for breast and for supply. Let's see the other one. Let's go to the data. Pay attention. We go into the data now. Oh my God. When you take a look at the data, we can see bottle, supply, breast. The one that arrow is showing is supply and breast, which means bottle is in the intercept. Does that make sense? Now, there are two things in the intercept right now. And the two things in the intercept now is a level of level of the sex and the level of the type of food. And that was why I said boys and bottle feed. When I talk about boy and bottle feed, I'm actually going to be referring to the estimate here in the intercept. Now, which is -1 point. That is what I put here. Can you see that now? So which means this guy now represent the probability, the probability model. Okay, it represent the logistic regression in probability form. Okay, now with this now, if I want to make a prediction, okay, with whatever I got here, will give me the probability. The probability of what? The probability of having disease, okay, given that is a boy and the supply is bottle. Does that make sense? This is going to give that probability, which is going to be a baseline. Okay. I can also use that to calculate, go back to the model to calculate the probability of the other one. Now, look at another question. How do we predict Y using a saturated model? Now, saturated model is different from fitted model. Saturated model is a theoretical model. And if I want to talk about theoretical model, I'm actually need to go back to the probability distribution of the response. If I want to talk about saturated, I need to go back to the probability distribution of the response. Now, if Y follow binomial, okay, with n, with parameter n and pi, okay, then the f of Y will be n combination Y, okay, pi raised to power that, 1 minus that, okay, 1 minus that, and of course, the expected value of Y will be that. Theoretical. That's a theoretical. So because I want to talk about saturated, okay, if I want to talk about, I said, how do we predict response using the saturated model this time around, not with the fitted. With the saturated model, okay, that is why I'm having this. With a saturated model, that's why I'm having this. Where do I get that? From a theoretical formula of binomial of the mean. It's n pi, okay? And n pi now is going to be n pi cap. Can you see that? If I have n pi cap, then what am I going to use? If I want to find pi cap, okay, and if that is equal to y high, okay, then if I want to get a pi cap, it's going to be y over n high. Okay, y over ni. Oh my God. For each case, can I figure out the probability of having disease? The probability of having disease will be the number of disease divided by the total. Now, and that was why I get 77 over 458. So 77 over 458, I'm going to take you back to the data set. 77 over 458. Please pay attention. Now here, I'm going to say the probability of having disease now is going to be 77 divided by the total for case 1, 19, divided by 147 for case 2, all the way to 31, divided by 464. Each of that represent that is a saturated. How to obtain the predicted value of the response using saturated model, which means the number of the estimate that I'm actually going to get here is going to be the same as the number of observations. And that was why I told you the other time. In a saturated model, the number of observation is the same as the number of parameters. Any question on that? Any question on that? Any question on that? Now, that is how to answer that question. How do we predict Y high using a saturated model? Now, the next. Now, some of you may not know, how do I actually run the code in R? Oh my God, this is the code. I'm going to write GLM. If you write LM, then you are just doing linear regression. It has to be GLM, and you have to indicate family equal binomial. Does that make sense? Now, we're using baby food. You can see the results that we have. Okay. Now, we want to move away from the saturated model to the fitted model. This is the fitted model. Okay. Now, the estimates here in the fitted model, they are called log odd estimates. Please pay attention. They are called log odd estimates. Log odd But you know what? Log odd is not easy to interpret. What do we normally do? We take the exponentiation so that we can interpret that in a odd ratio form. Okay, just letting you to know that. Okay, now where is the deviance? You're always going to see a deviance and residual deviance in the output. The null deviance 26.37529. Residual deviance is that. You can see here residual deviance is lower than the null deviance. Okay, then don't forget the null deviance is only comparing saturated, which is the best the theoretical model with intercept model, while in the residual deviance we're comparing saturated with the model with predators. And of course, here we're actually going to rely on the residual variance, but residual deviance. But they are trying to tell you the residual deviance that you got in the R output here, it is the formula they use in getting that. What the program behind the scene is this guy. Please pay attention. That was what the program behind the scene. Okay, two terms different between the likelihood of the saturated and the fitted. The fitted model, the one from the GLM, that is the logistic regression model you use. You're comparing that with saturated model, the saturated model where that will give you the estimate for each case, for each observation. Okay. Now I need you to pay attention. What would be the null hypothesis? What would be the alternative hypothesis? Oh my God. The null hypothesis would be that there is no significant difference between the fitted model and saturated model. But alternative hypothesis is that there's a statistical significant difference between them. Before we can start celebrating here, the p-value must be larger than the level of significance, because we don't want to reject the null hypothesis, because we want a situation where the fitted model will actually equate the saturated model. Now, if you take a look at here, the p guys, the p-value that we got is actually 0.69700062, which is greater than 0.05. If you want to go by passing, okay, it's still 0.72928864. If you want to go by this, it is that. So in each of different kind of, tests that we can conduct, we can see that the null hypothesis cannot be rejected, which means the generalized linear model, the fitted generalized linear model, perform equally with the saturated model. Is there any question here? Is there any question? Okay, and that was why I said, does our model fit the data well? I say yes. Yes, because the p-value associated, okay, the p-value that we conduct, not the p-value here. Oh my God, not the one here. I'm not interested in the one here, not the one here. Okay, because if I want to tell how good is a GLM, a fitted GLM, then I actually go to analyze deviance. So what am I analyzing now? I'm actually doing that for deviance. Okay, I'm actually doing that for deviance. Okay, so in each of these, the first one is calculating the probability of a chi-square will be greater than that. What is 0.72? 0.72192 is residual deviance. Does that make sense? And don't forget, the residual deviance is the one that compares saturated model with what? With model with covariate. And what are the covariate? Covariate is predator. What are the predator here? I'm talking about the sex and the type of food supply. Okay, now that's what I said. Any question on that? Any question? Any question? Now I want to move right now. I actually want to move right now. I said, which model are we accepting or rejecting? Now I'm giving you opportunity to say what you have in the H naught. Oh, saturated likelihood is the same as the fitted. We don't want to reject that. If we reject that, that's an issue. It means our fitted model does not perform equally with the saturated model. The saturated model is the theoretical model that fits the model perfectly well. Is there any question on this? Okay, I want to move to diagnostics. Oh my God. What is the difference between the deviance and diagnostics? You remember when we're dealing with the general linear model? I'm going to say that again. When we're dealing with the general linear model, where we're considering linear regression, okay? We also investigate whether the model is obey assumptions. Okay, we did regression diagnostics. Also here in the generalized linear model, we also want to do diagnostics. And the way we can do diagnostics here, okay, something you remember when we're doing diagnostics with the linear regression, I remember that time we standardized residual and we're able to get a Cook distance formula that is based on standardized residual to be able to detect if there's going to be a particular observation that could influence the result. So right now, okay, we can modify deviance and the Pising chi-square. Okay, so I said the deviance and the particle so allow us to introduce new type of residual that will enable us to investigate maybe outliers. We can also have issue with outliers here too. Okay, now, and that is what I'm trying to define. A residual raised to power D, the passing residual, the combination of that. I said after proper standardization of that and that can be used to identify outliers and influential points along with the Cook distance, which the GLM specify as equation 7. Please pay attention to that. There could be possibility of outlier too here. Okay. Now, I want to go back. So if you do that, which means, oh my God, with this, all of this, okay, we're able to derive residual plots, the normal KK plots that can also be used as diagnostic plots for GLM. Don't forget, we also have diagnostic plots for linear regression, right? The way those were computed or constructed is different from the way we're constructing this. Those ones in the linear regression, we base that on residual. But the one here, we actually base it on deviance. Okay, now you can see the residual plot, you can see the normal QQ plot, and all of that. Okay, that you can actually, tell us something. Now, lastly, how do we make prediction with logistic regression? How do we make prediction with logistic regression? Now, I told you the other time, logistic regression, we can have it in two form, either in logit form, that is in logit form. In logit form is when you have the log of odd ratio, or in a probabilistic form. Okay, now the pi, which is the probability of the presence of the characteristics of interest, okay, depending on the predator, could follow Bernoulli or binomial, depending on the number of observation. Now, suppose you've already, have your fitted logistic regression model, okay, either in logit form or in probabilistic form. How do you use that to make prediction? That's what we want to do now. I need you to pay attention. I said, suppose we may want to predict pi. If you want to predict pi, then you need to have your logistic regression in probabilistic form. Does that make sense? If you want to predict pi. Now, if you want to predict pi, okay, don't forget the first step. If I want to make a prediction, okay, of pi for a new observation like new predator, okay, new predator, okay, don't forget, I need to for estimate my beta, which is what you've done. When you run the logistic regression, the GLM in R, then you obtain the model. If you take a look at the second step now, is having your model in a logit form. I told you the estimate that you see in the logistic regression output, they are called log hard estimates, the way they appear. Now, if you solve for pi, you're actually going to have it in a probabilistic form. Okay, if you solve for pi, you have it in a probabilistic form. Now, if I know the value of x, since I already have my beta value, if I know the values of x, I can have a prediction for pi cap. But a prediction for pi cap is only going to give me one single value. That would be what? Called what? A point estimate, right? Point estimate. Okay. And you know what? So I can have an interval estimate for that as well. Now, if what I actually, if you take a look at what I have here, I need you to pay attention to the two. Oh my God. What is the difference between this guy here? Please pay attention. And this guy here. Because if you look at the first one is logit, the confidence interval for the logit, the confidence interval for the log odd. That is the first one. Okay, you know here, you're only going to get a point estimate, right? A point estimate for the logit. Y here is going to be the interval estimate. A point estimate could be wrong or right, could be low or high. And therefore, for you to have a way to rely on the estimate, that is the interval estimate for the logit. And the interval estimate for the logit, what are we using? Z-score, not T-score, Z-score. Okay? Now, what about the one for pi? You know, if you take a look at if you take a look at this guy, if you take a look at this guy, that guy will only give you a point estimate of the probability of maybe having the disease. Okay, a point estimate, just a single result that could be wrong or right. But you know what? Oh my God, this guy here will give you the interval estimate for the pi. Is there any question on this? This is how we can make a prediction. Now, this is showing you how we make, when you take a look at this, these two collectively they call point estimates. Point estimate, you're only going to have a single value. A point estimate could be wrong or right, because don't forget, the estimator, okay, will give different values. Okay, the estimator is a random variable. Okay, and that is the reason why we cannot rely on point estimate. We need an interval. So this guy here, the two of them represent the interval estimate, where we can actually say the true value of the parameter lies with the associated degree of confidence. On Wednesday, I'm going to start another GLM that we call Poisson regression model. You know, the one we finished today is when the response variable is categorical. But what if in a situation where the response variable is a count? For instance, I want to determine I want to look at the effect of some factors on, what make customers to go to a particular store. Okay, that's a count. Then the GLM model that I'm actually going to use for count will be a Poisson regression model. And of course, we're going to use a distribution called Poisson distribution. Don't forget, Poisson distribution also a member of exponential family. And of course, we derive the leaf function for that. We're going to talk about that on Wednesday. And because of the assumption of Poisson regression that talk about, if you look theoretically, Poisson regression have the same mean and variance, but that may not be realistic in a real world. We could have a situation where variance is greater than the mean, which will lead us to over expansion. On Wednesday, we're going to talk about Poisson regression model and the problem of over expansion. Okay, the over expansion that may, where we may consider how do we deal with over expansion in Poisson regression will also be discussed on Wednesday, where we could consider other form of regression type, negative binomial regression, and so on like that, or zero inflated Poisson regression, and so on like that. Statistics is like a story that goes on and on and on. Now, this is where I'm actually going to stop today in case there's anyone in this class who gets stuck. Make sure you reach out to me if you get stuck. I want the performance in midterm 2, the average to be 99. It is possible. You can make it happen. On Wednesday, I'm going to come to class with your exam booklets. Okay, this one is for a different class. On Wednesday, I'm going to give you back the exam booklet. Make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you.